Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
How are you all doing? Welcome to another episode of Ask Us Anything about Electrochemistry. Your host, Dr. Alex Paraff. With me is my co-host, Dr. Neil Spinner. Welcome to another episode where you get to ask us anything about electrochemistry. Last week we were out. We had a lot of stuff going on.
It's actually been like a month since you and I were sitting in this room doing this.
Oh yeah,
it's
that's
been
right.
a long time.
It has been a long time.
Feels like it's been forever.
Yeah. Trying to remember actually all the boilerplate stuff that I mentioned.
Yeah,
but
there's things.
Yeah. So first off, actually, we're, as you noticed from our slightly updated introduction, we are launching a podcast, and it's something that we've been working on for a while. So there's for YouTube members, tier 1, tier 2, you'll actually, I think it's just tier 2, you'll have early access to the podcast on YouTube. Starting, I think it's December
7th, I think.
December 7th.
Yeah, we should probably look at our own video.
We have to look at our own video and actually double check to make sure we have the right date.
It's like December 7th and then January 4th, I think.
Yeah,
those are the dates that are.
Yeah, those are the dates where the general release will be January 4th. But we're launching a podcast. We're very excited about it. And these Ask Us Anything about Electrochemistry episodes are always about trying to help you understand electrochemistry. We do a lot of YouTube videos, webinars, just calling us on the phone. People have lots and lots of questions about electrochemistry, fundamental and even some practical aspects of it. So sometimes it's not always appropriate, either during a webinar or on a YouTube comment, to try to answer some of these very technical questions. So we create these live streams specifically to take a deeper dive into your specific questions. So the format, generally, we usually go for about 2 hours from now. And just type in your question in YouTube if you're watching us on X or Twitter. It's a little tricky. I usually, if you write a comment, we'll try to keep an eye on it. Sometimes our software doesn't always update us on what questions come in. But there's probably going to be a little bit of a delay between when you write the question and when we actually answer it back. So keep that in mind. It may be about 20 seconds. We're using Restream as our broadcasting platform. And if you're a tier 1 or tier 2 YouTube member, you can join us on Restream and actually share your data, talk to us. You don't have to just type your answers in or your questions in. You can actually join us, talk to us. We can hear your voice. You can present some weird or messy EIS or cyclic voltammetry data, and we can actually talk about it. So the last few things to mention is there are no dumb questions. Electrochemistry is a very, very difficult subject, and that's why we do these. One thing that we have noticed, I think this is actually episode 30 of us doing this.
29.
29?
I think
we're
so.
super close.
Let me check actually, because I thought we were at 29. You thought we were. We're in that ballpark.
We're in that ballpark.
But I gotta figure that out.
In general, we have found that the way we're able to help you the most as scientists trying to understand some electrochemistry, there's kind of like two very broad extremes of questions. There's questions that are super, super, super general, like what is cyclic voltammetry or how to do cyclic voltammetry or EIS. And then there's kind of an even more high level of specificity, which is like, oh, what's the activation energy of this molybdenum oxide formation or something like that. Some of the answers to that are super specific. They're like hidden either deep in the literature or they are or they haven't been even done yet. They haven't even been done yet. That's where you as a researcher are trying to figure it out. And some of those questions we honestly would not know it because it's so specific.
Unless we happened to do our PhD in that topic.
Yeah, unless we did it exactly in that topic. Yeah. And even then, there may be some level
even
of
then I forget it was a while ago.
But then some of these bigger questions about like cyclic voltammetry and EIS that are just like what it is and how to do it, those require like hours. Like that's a full webinar. And if you are a tier 2 YouTube member, we do have full webinars on some of these topics. Neil has a 5-part EIS webinar series that you can access at any time as a tier 2 member. The questions that tend to be the best for us that we think would be most helpful to you is if there's, say, a specific aspect of a technique or even something relatively general about, like, say, a material or a metal or a process that you have confusion on. And those are things that we think we can answer very clearly. And we can actually spend 10 to 15 minutes really going into that in detail. So this is something we've observed over just the months of doing this.
Yeah, we've got lots of experience now, and really just throughout our careers, I guess you'd say, with these kinds of questions. And it isn't to say don't ask a question if you think it's too big or it's too specific. It's just that in some manner of thinking, you want to find the sweet spot between, like, tell me about electrochemistry. How long do you have, and how many years of school do you have left? Like, that's too big of a question. You know what I mean? And tell me about exactly what the electron was thinking when it entered the iron rubidium bisphenol complex, what its thought processes were at 2:19 p.m. on December 5th, 1997. Like, these questions are so specific that, unless you literally studied the psychology of electrons for your PhD, I can't answer that question. I don't know, and granted, like, again, feel free to ask if your question does get overly specific. We'll do our best. Or if we don't know, we're going to tell you we don't know. We're not going to make something up. I mean, we'll use the best of our knowledge and our understanding, and we'll look something up if we have to provide context. But that sweet spot is what we're looking for.
Yeah.
It's like,
and we think it'd be most valuable to you as well.
Yeah, exactly.
Yeah.
So to get the most out of our time.
Mm-hmm.
Now Barry is here and apparently is going to his office scrambling. So we're going to wait for him to go and get to his office. But in the meantime, there were a few questions because we've had a couple weeks off. Let's see here. So there was one question, I think earlier this week, actually here by Ruben Ferreira, that said, can you still achieve laminar flow in your low volume RDE cell, 8 milliliters? Does the proximity of the walls cause any disturbance? Typically, I see RDE being done in much bigger volumes. So what Ruben is referring to, which I will share with you, and believe me or don't believe me, that's your choice. We don't we're not really fundamentally interested in marketing our stuff. This is really supposed to be a educational thing. So I'm not doing this to say, hey, look what Pine Research has. You should buy our stuff. I promise. Yeah. But because the question was asking about RRDE in small volumes, this is a thing that we have, and so I'm fairly certain this is what Ruben was referring to. So this is actually an RRDE cell that I developed some months ago, maybe a year ago. I'm not sure
over a year ago.
Timeline. Yeah, it's been a year. Gosh, okay. But this cell is just what it sounds like. It's like you can do rotating disc electrode or rotating ring disc electrode experiments as low as 8 milliliters of solution. And so I basically developed this thing. I mean, you can really see it's just like a simple cylinder with 4 ports coming off the side. Right, there's an overhead view. That's a pretty good view of what you're looking at here. And I got requests for this cell over years, in part because people are working with like expensive electrolyte, right? And if your electrolyte costs $1 million for 10, 10 milliliters, it's like, well, I'm not going to do 100 milliliter solution of anything. It's just way too expensive, and your advisor is going to kick you out. So, so that was one of the reasons I wanted to develop this cell for folks who are working with expensive electrolyte, or frankly, just it's more economical if you wish to conserve, electrolyte and whatever, even if it's sulfuric acid, it's just less waste, et cetera. Okay. So the answer to your question is, can you achieve laminar flow? Yes. Does the proximity of the walls cause any disturbance? Not really. And typically I see RDE being done in much bigger volumes. Yes, you do, because that's sort of the standard. And typically the reason for that, as far as I can tell, I'm not an expert on all of the history of RDE, but as far as best I can tell, most of the reason why the volumes for our RDE and RDE experiments is 200 is a bit large, but the point is there, 70, 100, 150 milliliters, something like that, is because the size of the electrodes is bigger. It just is. It's usually, like the rotator and the disc and the ring and the shaft and then the reference and the counter electrodes just are a bit larger, and you need more space. And so the cells that have been developed, we have some, and a lot of our competitors have some, and there's a lot of glass, companies that develop these different versions of these kinds of cells. They have to usually be of a certain size because the electrodes are kind of large. And then, you can get into the idea that the hydrodynamics might be better controlled if you have like, rounded surfaces or not so sharp surfaces, things like that, which is to your second question, does the proximity of the walls cause disturbance? Right, because in theory, having a bigger cell, maybe I'll draw that too. Let me get my PowerPoint here. Make sure I'm sharing right.
Yep. Yeah. You're sharing. I'll make it a little
Start bigger. Inking. So, for example, if I have a cell, it's relatively rounded and smooth, right? Okay, and I have solution in here. The theory of it being that as my electrode rotating, this is the rotating, disc. There's my counter electrode. Here's my reference electrode. It's like if there's enough room in here, as I'm rotating this, I'm causing a flow of solution up, basically like a vortex up from the bottom, and then it sort of goes into, I'm drawing in 2 dimensions. Obviously, this is 3-dimensional, but I haven't figured out how to draw 3 dimensions yet, outside of SolidWorks or something. Anyway, the point is that you have this sort of, looping flow, and it's like the theory, well, if the walls aren't, are far enough away, like you don't have edge effects, like you have like a no slip boundary condition, and does that affect the hydrodynamic? You want to make sure you have enough room for the solution to flow. Okay, so the short answer to this is that even in a big cell like this, you can actually quite literally move this all the way down. We've done this. Our colleague has done this like a long time ago when we were just doing unrelated to this cell that I showed you before, but one of our colleagues actually did this test just like out of curiosity, or there was perhaps a customer reason. I can't remember why he did this, but he filled with like 1 milliliter, such that it was almost like a hanging meniscus experiment. Like he put like a drop of electrolyte down here, and he somehow got The other electrode's barely in solution.
Wow.
And he rotated this thing and he saw hydrodynamic behavior. I mean, it's incredible. It's like, I don't even understand how that seems even like what, like 1 milliliter or half a milliliter, like you still can get the behavior. So the point is that this laminar flow dynamic, it just doesn't appear to require tremendously large volumes. And so if it works with 1 milliliter or even half a milliliter, it certainly works with 8 milliliters. And even though the cell is small, like it's physically small, you saw it. I mean, it has this hex base and it's, it's got these ports or whatever. And this is pretty small. And it's like the diameter of the electrode is, this space on either side is not really large. It's still actually plenty of room for that hydrodynamic flow, like circular or whatever laminar flow to develop, and it actually forms quite well. And it's the 8 milliliters is actually larger than I was aiming for. I was going for 5 or lower, and I in my testing of this cell, I realized that I have to do 8. It's like the solution, like 5 is only like up to here, and then your counter electrode like isn't in solution yet, so you have to add like 3 more milliliters, and you finally get. It's just that's just sort of what it is. It's like as you start filling this cell that I showed you, it's like the liquid level gets to a certain point and then everything's in solution. And until then, it kind of isn't. So the last thing I'll say on this, which is just to prove it to you, I suppose, is I'll show you the data that I took with that cell. And I'll show you that you get the hydrodynamic behavior you're expecting. So this was some data I took. You can see May of 2022. So it's been a little while. And I did a bunch of testing with it. I mean, I did stationary CV. So this was not hydrodynamic, not rotating, but you can see very clean looking CV in a very, very small a volume. And then I did RRDE. And so I did, 400, 900, all that kind of stuff. And I put it together so you can see like the data. It was not perfect, certainly typical kinds of pitfalls of RRDE stuff I was not immune to. And it's one of these things that people do ask from time to time, like, oh, why isn't it perfectly flat? And there's like 100, 1,001 reasons for that. But I mean, basically you can see the kind of spacing you expect to see with the square root dependency, whatever the rotation rate. Exactly. Right. Yeah. And disk and ring looking about as you would expect for a 30-40% efficient thing. Like, I'm glossing over a lot of like facts of RRDE stuff just for the purpose of showing you that this does work, and you need not be just, concerned in some sense, like, oh, well, what if my laminar flow isn't developed or whatever. Now, getting the it's physically harder to mess with a cell that's that small, like small volume stuff is just, it's harder. Like it's physically harder. You have to have good dexterity and get all the electrodes in and adjust them, like those are real, just normal world challenges for any of you folks who have done electrochemistry on small thing, small things, right? It can be hard. Okay. But certainly it works. And anyway, hopefully that's, some answer or validation for you if you're watching this now or you tune in later. Ruben, I think that was the name, right? Ruben?
Yeah,
yes,
I
Ruben.
so.
That this actually is quite possible at really low volumes. So if your electrolyte does cost $9 trillion per milliliter, whether you use that cell or you just try making your own little beaker or small thing, your advisor will not fire you because you can use like a few milliliters and get some good RRDE.
Data, yeah. And a lot of people want to use like ionic liquids and stuff like that are super expensive, and they want to do RDE in it. So it's very good for that. All right. It looks like we have a question, kind of a 2-part question from Race. Somewhat open-ended, but let's go through it. Hi guys, does CV, so liquid voltammetry, provides a different perspective compared to galvanoscopic charge discharge and EIS? He then continues to ask, presently we are doing much more galvanoscopic charge discharge and EIS, but not so much CV. Thanks. So I think this usually, I want to say this has to do with batteries. Like if you're doing galvanoscopic charge discharge, and EIS, you're more likely than not studying batteries, and that's
Yeah.
that's probably the most common techniques. But I don't know very much if, like, I know a lot about CV in like 3 electrode systems, but CV in a battery, I'm not so sure it's going to teach you that much stuff.
It's not generally advisable. You can kind of think of it as in terms of so if you're doing galvanostatic charge discharge, right? One of the more common scales is like 1C, which is where you charge it from 0 to 100% in 1 hour's time, and that is associated with a certain amount of current or capacity, right? So if you're a battery person, you probably understand this terminology, and if not, it might be a little unclear, but you can think of it as your phone or any other device or whatever. It's like it will be charged or discharged over a certain amount of time. And it's like if you're charging up your phone, you know, the fast chargers now that take 30 minutes or an hour or something. So all of that is to say the voltage is moving. How to measure charge storage capacity through CV? Is it accurate? Okay. So
we're talking about the same thing, kind of.
Yeah. Well, I'll continue this thought because it is sort of relevant, and it's sort of explaining why CV isn't the best way. It's not the best way to do it. Yeah.
Yeah. So that's just building up because it just says that Rasmus just said how to measure charge storage capacity through CV, and is accurate, but it looks like we can.
Oh, that wasn't Race. Oh, it's an R name with the same color circle, but it was a different person.
Yeah, okay. Yeah, it was a purple.
But this is exactly.
I'm like, still kind of similar.
It looks like the same. Yeah, different person, same exact icon. Okay.
Yes, just a different shade of purple.
Different shade of purple. Yeah, so that threw us. Okay, anyway, sorry, but these are related questions. So, more to that point, it's not often you conduct a cyclic voltammogram in like a normal, quote unquote, 3 electrode system, and it takes you an hour to scan over your limit, right? That's a really slow CV.
That's very slow.
Right? Yeah. So one way to think about why you wouldn't normally do CV, okay, is because if you do a cyclic voltammogram at any like reasonably appreciable scan rate, like 10 millivolts per second or faster, which is what you would do. 10 millivolts per second is usually like pretty slow, right? For like a platinum thing, right? Yeah. Exactly. Just do a little math here. If you're working over like a 1 volt range, right? 1,000 millivolts divided by, even 1 millivolt per second. Let's say you go 1, that's pretty slow. 1 millivolt per second. It's 1,000 seconds divided by 3,600 seconds. So that is like what, 30% of an hour? How many minutes is that? This is hard math. It is 16 minutes.
Yeah. And that's just one direction.
Right. One direction. So doing, for example, if you have a 1 volt, like range of like from 3 to 4 volts is like 0 to 100% charge or something like that. Right. One way to think about this, and I'll explain to your question, Ramzan, why it's not particularly likely to be accurate, is that going from 3 to 4 volts at 1 millivolt per second, which is a very slow scan rate, is basically like the same thing as charging up a battery in 16 minutes. That's quite fast, right? That's like 4C for terminology for those of you who are battery folks. That's a fast charging rate. And when you're determining the capacity, you typically don't want to scan super fast. I mean, you can see what the capacity is at fast charge rates. And for example, when you charge or discharge a battery really fast, typically the capacity will be lower. It won't be as reproducible or repeatable. The efficiency might drop, and it might degrade faster. Its maximum capacity will degrade over time faster than if you charge and discharge very slowly. So one of the reasons why you don't typically see that as often is because doing a CV is like charging a battery really fast, even at slow scan rates. And Ferris has just added, typically they do 0.5 millivolt per second, right? So sometimes people will scan even slower. And then when you do that, it's a similar discussion. Okay, so maybe not 4C, now it's 2C. Still pretty fast. Okay, so all that is to say that in general, I might argue it's not the best way to do that, because to get the capacity, then you basically are just integrating your current over time. That's charge, which is it's the same as capacity essentially. Okay. And it is frankly easier and just more common to pick a current and apply it evenly for a set amount of time to charge or to discharge a battery, because that's the other part about the CV. You know, when you do a CV, the current is changing all the time. So it's actually your charge discharge rate is changing constantly, because your current is changing constantly. So you're actually not charging a battery in any kind of uniform way. Now, perhaps to play devil's advocate, or to Ferris's point, which he says it takes ages, of course it does, and it can show some useful stuff. So one of the things that you can get from a CV is just the normal things that you would get from CV, which are peaks, and you can get like a potential peak position at which part of the intercalation process is occurring, or the SEI formation. Like you can identify, in the same way that you can with any CV. It's just that it's not always, those are not always, it's not that it's not interesting or like relevant or useful. It's just, it's not as often a metric that is as practical. I don't know how to put it. It's like, okay, so like the SEI occurs at exactly this potential or something, or the charge discharge, but it's like mostly you're just trying to see how well and how stable this thing acts as a battery over whatever period of time. And so you're just trying to charge it and discharge it. You're trying to do impedance to, discover how the capacitance has changed, or the resistance has changed, or it's degraded over time, or any of those kinds of things. Doing CV is like a way to non-uniformly charge up or discharge a battery while just observing where the peak locations. Like you wouldn't likely do a long-term CV study the way you would degrade a catalyst material for like a fuel cell, for example, by doing CVs like 10,000 times and seeing how it changes. Like that's not what you would do with a battery. You would just charge it and discharge it with a constant rate. Because it's frankly harder to draw some conclusions when the charging and discharging rate is non-uniform. It's like, well, it degraded this at this fast after I charged and discharged it a bunch of times. Well, it's like, well, how fast did you charge it? Because that might make a difference. Well, I don't know. I did CV. So half the time it was at 10C, half the time it was at 0.1C, half the time I was adding a ton of current, half the time it was in a lot of current. It's like, well, I don't know. What's the reason it degraded or didn't degrade? It's like, you kind of can't necessarily pinpoint that easily. So that's the best I can give you, is that maybe a little bit of both sides, trying to be fair here. I hope I kind of explained why it's not exactly the tool to use for batteries, or not used as frequently. But to Ferris's point, for example, you can see peak positions and maybe some of those things, that any CV would give you, and that can be maybe instructive or educational.
Yeah, I'm just thinking, because I'm no battery expert, so I may actually ask a question before we'll get to Barry's question.
You can ask me anything about electrochemistry.
I can ask you about anything.
It's in the
so
title.
because one thing I'm thinking about, like whenever we do cyclic voltammetry, we usually are looking at maybe some redox process, and we start at a potential where like nothing's happening, like it's just non-Faradaic current, and then we sweep and scan through an area where like we hope to see some Faradaic current. But like I'm assuming with a battery, you're always working within a potential range where like stuff is happening like almost all the time. Like,
yeah,
you're not taking, like, I'm assuming with a lithium ion battery, you're not starting at 0 and going all the way to 4 volts or something. You're starting maybe within a small range around 4.
So you actually do, when you're looking at a half cell thing.
Okay.
So what you just described is something that can be done. For example, when you're studying just the anode or just the cathode, you can, for example, do like a CV over a wider voltage range to look at, where the intercalation process happens or what have you, in the way that you would with a CV. But it's, it is more of an exploratory kind of a thing.
Yeah.
Right. Not to say that there aren't quantifications, but usually those are like by scan rate.
Yeah.
And there isn't a lot of instructive, process to like doing a scan rate study with battery stuff, because that just means you're charging faster and more non-uniformly, and all kinds of odd stuff might happen. It's not really designed for that. But you can do stuff like that, like scan between like 0 and 3 volts, because that's like the potential of Li plus. It's about 3 or whatever it is, and it's like with a like a graphite or whatever, you get the SCI formation. So here's the devil's advocate exception to everything I said. Don't use it. It's like, one of the things you can do, for example, is load up a cell with a bunch of graphite of some kind, and like a lithium as the counter or the cathode, sort of, whatever terminology you want to use, and do a couple of CVs, like 3 or 4 at really slow scan rate back and forth. And you'll see like huge peaks in the beginning and huge amount of current for the SEI formation.
Okay.
Which is like a degraded layer of electrolyte on top of the graphite. And then like the second or third or fourth CVs you do, the current won't be there anymore because the SEI is already formed. So it's like, sometimes that's one application of it, is to like observe the SEI formation. And that's one of the things, for example, like most people it isn't, I suppose I should say, it's not obvious still or known with 100% certainty what the solid electrolyte interface layer is. Nobody really knows exactly what it is. It's like some odd decomposition of electrolyte. It's like a film of stuff that has been decomposed that helps prevent further decomposition. It's an odd concept, but it forms. It forms on carbon mostly. In batteries, and it's absolutely critical to the functioning of batteries. And so anyway, the CV of that is a way to like observe that process and get some fundamentals about it. So I guess the fundamental or I don't know, overarching answer to this question is, it's like, yes, it does provide a slightly different perspective, and it isn't precisely an either or proposition, right? I think that galvanostatic charge discharge and impedance to a large degree are almost completely needed and critical when doing battery testing and analysis, and CV is not, but that isn't to say it couldn't be a supplementary kind of test that helps you elucidate some information, like on the SEI or what have you. So there's an overview of cyclic voltammetry and batteries for you. Hopefully that's helpful.
Okay. All right. Well, I learned something new too. Everyone can learn something new. Just checking if there's any.
I think Barry has a question about something.
Let's do it. So Barry, thanks for waiting. In chronoamp, the slope is linear non-zero. How much is this diffusion of redox species into DBL, diffusion layer, and
double layer?
Double layer. Oh,
Okay.
double layer diffusion into double layer. Yeah, I mean, I'm usually used to thinking like
I don't know if
CDL.
it's
That's right. Double layer. And how much is the increasing size of the double layer diffusion layer? And then let's see, he's just talking about in the long time scale, not at the beginning step. Okay. So slope is not how much is it? So I guess I'll just kind of draw a picture, and maybe we can kind of talk our way through it. But let me go. So usually when we're doing, is my screen good? Okay, good.
I might make the question go away so we can see what you're drawing.
So normally when we do chronoamp, let's do a long time thing, because I think that's what Barry's talking about. You have current on the your chronoamperogram will have current on the y-axis and time on the x-axis. The potential step that you apply will look something like this. And if this is t equals 0, you're here, and then you step the potential up, right? And then you hold it. So, and typically what a chronoamperogram looks like is this is 0. Let's say this is 0. And then we have this huge spike. And then there's this very slow decay. It's not linear. It's kind of an exponential decay. And it constantly is going down and down and down and down. And so in Barry's, so this is like what the picture looks like. And it looks like Barry is talking about like long time scale. So he wants to know about all the stuff that's happening kind of in this region. That is what I am.
He said it's non-zero slope though. So it's almost like, is it,
so it's constantly going down?
I guess, I mean, I guess you can clarify, Barry, because if it's non-zero, but it's always a slope, does it cross 0 and go from positive to negative? Because that would be odd.
Yeah.
But like, presumably if it's
let's say this is
a non-zero slope, eventually it will hit 0, right? Or is it just a very, very small slope? And so it would hit 0 event, but it doesn't, or does it go back? Is it going up? There's some questions here, I suppose.
Yeah.
Because
Yeah. So like ideally, so actually let me erase this. So all of this current kind of in this region, right? Like I'm just going to highlight this green so people can see like all the current in this region, it's all diffusion. It's all just like
double layer capacitance. Yeah.
Well, there's double layer capacitance is relatively constant, sort of say. Like there's no more additional, like the double layer charged back here.
Yeah.
Like this is where it charged. Its time scale is so much faster than that of diffusion. So like double layer capacitance and any current associated with like going through uncompensated solution resistance, that all happened here. Actually, the height of this current, most of it's actually Faradaic current. So of course it depends. It also depends at what potential, like what is this value? Like what voltage is this? Because if this voltage is sufficiently high enough or low enough in potential, depending if you're doing an oxidation or reduction reaction, if this is sufficiently, let's just say you're doing an oxidation reaction, you apply a sufficiently positive enough potential. Most of the current here is Faradaic, but it also consists of some, it actually will consist of some double layer charging as well. And all of the decay is all, it's all diffusion. So it's just, when we get to this region where it's pretty flat but non-zero, we're talking about diffusion from molecules that are super, super far away, finally making it to the electrode surface and actually undergoing an electron transfer. And really, all of the current that you're measuring in this region, it's all based on the Cottrell equation. So I don't remember the Cottrell equation exactly, but it has a t to the minus 1/2 dependence. So it has some t to the minus 1/2 dependence. So over time, it's just getting smaller and smaller and smaller and smaller. But it might not actually reach 0 because there's still one molecule that's super, super far away that like manages to get to the electrode surface and hit here. So that, let's see, I don't know if Barry has a kind of any follow-up. If it's all
yeah, he also said he's in another meeting, so he
okay,
might not be able to comment much. But I think you basically answered his question.
Yeah,
right?
it's all diffusion. Yeah, basically.
And I guess the point to that is that the observation that it's linear and non-zero is not entirely accurate. That's just what a t to the minus 1/2 looks like at long time.
Yeah, that's right.
Because it's it's the Cottrell equation is I is equal to NFA C to the something
diffusion
over the square root of pi t, something
like that. Yeah.
Right. The point is that when you have t being large, it looks like very slowly sloping down something or other, right? But it's actually just the Cottrell equation, which is diffusion. It's entirely diffusion.
Yeah, it's entirely diffusion, and
exactly.
The only kind of inaccuracies are at like very, very small t. So all the stuff in this region will mess up the Cottrell equation, but when you're all the way down here at long t's, I mean, I'm talking like, tens to 20s of seconds, you'll
Right.
usually it should start looking pretty flat.
Yeah.
So yeah, that is that. So it looks like that answered Barry's question. But of
Yeah.
course, we could always we can also do follow-ups because he's in another meeting.
Yeah.
He's scrambling for stuff.
Hopefully I think that kind of addresses what he was after.
Yeah.
I think we missed. Did we miss? No, that was Barry. We're good. Okay.
I think we're good. That Chris is here. Hey, Chris. Essentially, partial passivation of forming.
Yeah, that was just related to the SCI thing I was talking about before.
Yeah. So there's a question by Max. All this stuff is actually all related to batteries.
Of course it is.
Of course it is.
Yeah.
Max Ferrer is asking how to obtain a reliable potential window on battery type materials in CV, GCD, and EIS analysis.
So EIS isn't going to help you to find the potential window.
I feel like CV is really the only one.
Well, yeah, CV and galvanostatic charge discharge are either or will help you. So let me show you. So CV, just like we talked about before, is an exploratory kind of a technique. Exactly right. So part of what my whole previous discussion where I was talking about why it's not as necessary or used perhaps in battery analysis, and part of the reason for that is that you typically know the potential window. Like when you're a lot of battery materials, what you're using some material that is in the literature, or you can infer from thermodynamics what the potential window should be. But of course, there are cases where you don't know. And so in that case, yeah, for sure, you would be able to use cyclic voltammetry to figure that out. And, in the analogous case of an aqueous solution, it's like if you scan over a narrow window, you get some nice looking. I'm neglecting any Faradaic processes, right?
Oh, yeah. We'll say there's no.
But then you increase the limit eventually, and Alex has talked about this on many of the live streams before. You increase the window, it'll go down really far. Okay, fine. And then when you increase the window the other direction, it will, shoot up really high. And it's like, okay, well, this is a way you do CV, and it's like, okay, well, I only want to scan between here and here, because eventually in all materials, basically, you have a solvent limitation. This solvent window might be plus or minus 1 volts for aqueous.
Yeah.
Okay. And then non-aqueous, that's not a C, that's a parenthesis.
I know. Parenthesis.
I see what you did there. That's an excellent dad joke.
Excellent dad joke.
So apologies for this messy, terrible handwriting. So for aqueous, you have maybe plus or minus a volt. It depends on the solvent, but anywhere from 2 to 4 volts. For non-aqueous, I don't know, something like that. Okay. So the point is that you can basically do some sort of exploratory CV, typically slowly. The other way is to do galvanostatic charge discharge. You can certainly do that as a means to figure out your voltage window. So if you set up a battery, a system, a cell, whatever, and you have it, with your unknown material, this is time and this is voltage here. It's going to have some open circuit potential, perhaps open circuit voltage when you create your cell. And so you just set some current. Now, this is the part where it's tricky. You're going to have to just guess based on the mass or whatever. Maybe you know the capacity, maybe you don't. Maybe you're just chucking some material into a thing and seeing what it does, and you want to know what the voltage limits are. Apply some amount of current, right? Is X milliamps or microamps or something. And you might just start watching the voltage go up, and it might go up or whatever. And it's like, what you're looking for is for the voltage to just like do that. Because once it starts shooting up like that, it's no longer charging. It's like this lag in the voltage in some way is when that's the equivalent of a peak in CV or something.
Oh, yeah.
Right? Like when the voltage is lagging, some process is occurring. It's like the current is doing a thing. And that's like the equivalent of a peak during cyclic voltammogram is when the voltage lags as you're adding current. That's sort of it. But once this starts shooting up, and then similarly, if you apply minus current, it's the same thing. It's like you're going to watch for lags or whatever. This wouldn't go back up. I'm just terrible at drawing. And eventually, it's going to like fall off a cliff. So it's like the voltage window you're looking for would be between where it falls off a cliff or shoots up a cliff. So that's how you would use GCD, galvanostatic charging or discharging, to determine a voltage window. And sometimes you get into a situation where it just lags forever and ever and ever, and it never falls off a cliff. That's probably because you are destroying your electrolyte endlessly. Stop testing that battery. That battery is garbage. Something is wrong. Sometimes that does happen.
Yeah. Okay, very good. Very good. There was a question. Actually, someone was interested in asking a question on Twitter, and I'm still waiting. He asked it like 14 minutes ago, how to ask questions.
Yeah, I wish there was a way to do. I don't know if it's a limitation with our technological incompetence. Certainly a possibility. Yeah. Or it's a limitation with Twitter itself, which I think and hope it's that one.
Yeah.
I don't know if video on Twitter, it's relatively new feature as far as I am aware, that like long form video and live spaces or streaming. I don't know exactly what all these different things call things, different stuff. Anyway,
but I'm keeping an eye out. So if you are asking on Twitter,
the point is, if you're on Twitter or X and you want to ask a question, probably best if you come to YouTube and type it, because it isn't clear to us that this whole setup we're doing gets questions from that platform to us, but the YouTube definitely works. So all these questions we're reading and showing to you are certainly from YouTube. So if you are on Twitter or X, thank you. And if you just are watching us and enjoying the content, we certainly appreciate that. And I hope you are. But if you had a question you want to ask, either join us live on Restream as a YouTube member, or come to YouTube and type a question.
Yeah. Speaking of YouTube member, thank you, Amin Yidrim, for joining us as a tier 2 member.
Awesome.
Saw that come on. So thank you. And you're more than welcome to join us on Restream and join any of our webinar content, and you'll have first access to the podcast when it comes out in December. So just keep that in mind.
Yes.
All right. Let's see.
Race had a follow-up.
What
do we got here? So EIS already provides insightful information on SEI layer. Yes, it does. Charge transfer, intercalation, deintercalation. So what makes CV useful here? Yeah, no, it's honestly
nothing.
Nothing at all. Yeah. Well, that was, I'm trying to.
You already got all this information.
I'm trying to be fair here because, there are people that have publications with cyclical tamograms. And I mean, I did it when I was in graduate school. Like I did a little bit of cyclical tam, not a lot, right? And most of my publications didn't have any CVs. If I did, I had one CV, maybe. Sometimes you'll see that it's like one, and it's just kind of like I don't know how else to describe it. It's like a lay of the land, right? It's like, like I'm studying this silicon material as an anode, as a possibility. Okay. And so the first test that I do, or like, I don't know, here's an example, like lithium sulfur batteries. It's lithium sulfur batteries. LIS has like 900 trillion oxidation states. It's like LIS and then Li2S5 and then LIS9S2S, Li15S. It's like, it just does. It's a crazy thing. I've never worked with lithium sulfur batteries personally, but I've seen some literature on it, and it's wild. Like it goes through so many oxidation states. So it's like, I think that like a CV is a way to show like, here's like 43 peaks. Cool. That's like a lay of the land. It's like, here's all the processes that are occurring or whatever. So I think the point, Race, is not to sort of look at it as like, well, I can get information about the SEI, using impedance, and possibly even galvanostatic charge discharge. Like, for example, the first charge or discharge you do will have a much higher capacity than the subsequent ones. And that's also giving you insight on the SEI formation or stuff like that. So yeah, it's not an either or thing. It's more like what makes it useful. I mean, it's a supplemental technique to look at some of the same processes, Again, my initial answer was that it's not all that useful and it's not used that often. So I'm kind of with you here. I'm just trying to kind of play devil's advocate, like, well, you can still use it. But I guess I still say my initial answer, which is kind of what you're proposing here, which is like, well, what makes it? Well, it's not the most commonly used technique for batteries, and there's the reason why, which is mostly the reasons I, described before. So, again, just to reiterate, I don't know, one part of that being that you can study the SEI formation within CV, but you're studying it in like a non-uniform charging way. Typically people are studying batteries while charging or discharging in a uniform manner.
Yeah.
And by forming the SEI or doing the charging or the discharging with cyclic voltammetry, you are fundamentally doing that in a non-uniform rate, right? That's fundamentally the case, because the charging and the discharging of a battery its rate is determined by the current. And cyclic voltammetry is a controlled voltage technique, which is why galvanostatic techniques are typically more preferred for batteries, because you're controlling the rate at which it charges through current manipulation, not voltage manipulation. So it's better to control the current and watch what happens to the voltage rather than the other way around.
Yeah. So we have a question from Twitter. I just added this question to our
very
captions.
nice.
So I'm gonna
okay. So it was like I should just open Twitter too, but was it like a comment on our post? Is that how that works?
Yeah, the person just replied, "Hey, at Pine Research," and then they have this question. So this is a question from Umar Latif. How do you compare the positive and negative potential scanning in CV? Some materials are scanned in positive potential and some are scanned in negative potential. What are your views about it?
My views, I'm for it.
Vote
for me. I don't know. Sorry, that's just a bad joke. Sorry.
No.
Please proceed.
No, absolutely. Yeah. So we're gonna just assume a couple of things. We're gonna be talking about like the IUPAC method or convention for plotting. So positive potentials are associated with oxidation reactions, and negative potentials and negative currents are associated with reduction reactions. So when you're comparing a positive or negative potential, you're trying to induce, like a positive potential, you're trying to induce an oxidation. So you're trying to remove an electron from the molecule in question. And if it's a negative potential, then you're trying to inject an electron into that molecule. So of course, I'm assuming you're doing like solution phase. But even if you had some other material, right? Because you're talking about some materials are scanned positive potential, negative potential. It's which direction do you want the electron to flow? Generally speaking, which way are you applying an electromotive force? And so also, if you hear a motor behind us,
what is that? Are they mowing the lawn, or is it a leaf
blower?
blower?
It's a leaf blower.
Oh,
There's like a leaf blower right outside of our office. They just show up.
Yeah, I don't know if that comes through. We have pretty powerful microphones, so maybe it does.
It might come through. Just a warning.
Yeah.
Now, one thing that a lot of people mistake when they're scanning is they will see. So actually, let me just show you on. I'll just draw a CV. This is something people are commonly confused about, which is that when you have a cyclic voltammogram, and let's just say this is positive, right? So let's say this is zero current, and this is voltage, and this is all like positive voltage. So let's just say zero's here. And so everything here is positive, positive, positive. We have some oxidation, and then go back, and then we have some reduction. What people commonly get confused about is they just do not understand, hey, why is it that I have positive potential, but I'm getting negative current? And it's because this has to do completely with mass transport and diffusion of molecules. So in this forward sweep, we were oxidizing some species, but then we moved to a potential, literally like this point or the points down here, right? We moved to a potential where the potential was not sufficiently positive enough to keep a molecule near the surface to be in its oxidized form. it was thermodynamically more favorable to be in its reduced form. So, or for that reduction reaction to occur. So that's something that I've commonly have seen people get confused about, because like I'm scanning positive and I'm scanning negative, which with different directions, and I'm in a positive potential or a negative potential regime, but I'm getting oxidizing or reducing currents, and sometimes that doesn't always make sense. You can get a lot of reduction current if you add a molecule to your system, and the potential is one such that, hey, this molecule should be reduced, even though you're in a positive potential. And the potential is always with respect to a reference electrode. So just some reference electrode, and that can be somewhat arbitrary. So it's positive with respect to one kind of, or it's positive with respect to one reference electrode, but it could be negative with respect to another reference electrode. So when that happens, it ends up, it can be very confusing how we think about positive and negative, oxidation, reduction, stuff like that. So I guess the answer to my question is, what are my thoughts, my views on it? It's confusing, but these things can happen. So hopefully that's,
and that last point is also one of the key, ideas about this, is that like it's positive against one reference and it's negative against another. It's like potential is fundamentally relative, so like 200 millivolts doesn't mean anything. It's like against what versus what with respect to what, right? So like, the whole like whether 200 plus 200 lines up with plus this much current or plus 200 lines up with this minus current. It's like, well, that change the reference and then it's minus 100 versus something else. Does that make you feel better? That minus goes with minus. It's like, it's all arbitrary, right? So you can shift the x-axis and it's completely arbitrary based on what your reference is. So everything Alex described about the thermodynamics of where you're at to have an oxidative or reductive species present, that's the key about whether you get, a peak in one direction or the other, essentially.
Nice. Yeah. Okay. All right. Moving forward.
See here.
Got another question.
Fernando has asked, I made a porous screen printed electrode for heavy metal detection. The expert explained, I hope you don't mean me, explained the impedance as RC couples, so like Randall's elements. You added a Warburg short, I assume that's what you mean by a WS, resulting in a significant decrease in the chi-squared, 100 times lower. Is that enough to prove him wrong? Absolutely. Yes, I'm serious. Yes, the answer is yes, it is. Let me clarify. Okay, I would not word it that way. I would not word it as you're proving him wrong. What I would say is that's probably enough to make the case that your model is better, that your interpretation of the data is better. It's actually a superior model. It doesn't mean that he's wrong. It doesn't mean that perhaps fitting a couple of semicircles with RCs is wrong. It's that you have used a circuit element that more accurately describes the phenomenon. And especially because you mentioned it's a porous SPE, which means you fundamentally have some diffusional process through a fixed length. That is precisely what a Warburg short is designed for. And so if it's fitting your data accurately, then most probably you should absolutely feel emboldened to say, maybe don't say you're terrible and I'm better. That doesn't make people feel good.
Yeah.
But for sure, if that is what you're seeing, you should feel perfectly emboldened to say, hey, Mr. Expert or Miss Expert, I believe that I have a better model for this. I believe that I have found a better way to represent this data. And here's the reason why. It's a porous material. I know its thickness, and I've used a model that is encapsulating that exact process, a Warburg short. And it fits, it even fits the data better. So yes, I do think if the information you've described to me is as you say, then yes, you should feel like you've got a better EIS circuit fit than just a couple of Randall's elements, for sure.
Hmm.
Let's see. Ramzan has a few additional questions here.
Yeah.
Looks like it's a multi-step one here.
Yeah. Let's talk Ramzan.
Yeah,
Okay.
let's see. So I'm working on synthesis of thin films for electrochromic devices. I've observed that cathodic current density increases more than anodic current through cyclic voltammetry.
Okay.
Okay, let's see. But the diffusion kinetics of the intercalation, deintercalation remain almost the same of both films.
Okay.
Okay, let's see.
There's more.
I have to think about this a little.
Yeah.
So I'll just get through all the questions and then. How can you interpret these results if only cathodic current density improves of the material? Is it not ideal if both current densities are equally increased? Okay, so thin film materials, in one of the current densities is increasing more, but the diffusion kinetics is kind of. Do you mean like diffusion and kinetics? Like those are
yeah.
Those are different processes.
They can be different. So there's a couple things. So here's a couple ideas, thoughts. So yes, first let's identify that diffusion refers to mass transport, the movement of molecules. There's a kinetic element to it, but then there's the kinetics, as in just like, all right, like how fast is the electron transfer, right? So now another thing, I'm not 100% sure. Of course, you know your data best, but are there chemical steps? Is there irreversibility in some of these things? He's observing more. And another thing to keep in mind is that the potentiostat always measures net current.
Yeah.
So you may have, there may be more, you're seeing more of one process than another, but it doesn't mean the other process isn't necessarily happening. It might just be getting kind of evened out by another process, if that kind of makes sense. You're always measuring the net current. Additionally, when you're doing things like cyclic voltammetry, you can have current associated with other processes those processes are not symmetric. So double layer charging, for example, may also be showing different levels of current that you're measuring.
Yeah, so it's like the intercalation deintercalation process is the same, but there's other processes that are giving you that asymmetry.
Yeah,
like other whatever unrelated processes.
And additionally, like there are other, you may want to consider their equations. Like when you're doing cyclic voltammetry, you can use the Randall-Sevcich equation to determine the diffusion coefficient for one direction of the CV. It doesn't always work on the other direction. So the diffusion coefficient for, if you have the diffusion coefficient for the anodic process, the cathodic process might be different. You may actually need to do a separate experiment where you start with purely the anodic species, and then you move to allow it to diffuse and measure the current. So these are just some ideas to kind of throw out there. I don't know if you're studying an electrochromic device, you could use some light or some spectroscopy to also support some of the kinetics that you're doing.
Now you're talking.
Yeah.
Spectroscopy.
My jam.
That's your jam right there.
Yeah.
That's
all right. Let me just check if there's something on Twitter. It doesn't. Okay. I have another thing from Twitter. I will get.
Nice. While you're doing that, let me answer the question about square wave, because I actually have a presentation I can use to illustrate some of that.
Oh, sorry. I meant to edit.
Square wave. Okay. Give me 1 second here, folks. There's a question. Okay. Square wave. Just so everybody is aware of what square wave actually is. Did you put the question in?
Yes, okay. I did. Do you want me to?
No, I'll yeah, sorry. I mean, it doesn't really. I just got it ready, so it was taking me a second.
Yeah, go ahead.
So Amar has asked how to choose a particular pulse amplitude, frequency, and step voltage scan rate. So basically, it's effective scan rate if you think about it for an enzyme immobilized ferrocene self-assembled monolayer. Is that what that is? On gold SPE using square wave voltammetry. How much scan rate is too much? So what I want to do. Okay, how to choose a particular pulse amplitude. I don't know that I can exactly answer your question as it relates to the enzyme immobilized ferrocene self-assembled monolayer on gold. Like, I don't know. This is back to our like original point. Like, I don't have a lot of specific knowledge of that system exactly. Okay. But I can at least try to answer in terms of what is square wave voltammetry and how the parameters are selected. So for those who aren't aware, square wave is this. You basically go up and then down and then up and then down and then up and down in an increment. Okay. So the parameters that you're asking about are the amplitude. So basically you go up and then down by that same amplitude, or you go down by double the amplitude. So it's like if you have 20 millivolt square wave, you go up 20 and then down 40. So it's like from wherever you start, you're going up and then down. So that's amplitude. The period is the time it takes for that whole thing to happen. Okay. And then the increment is how fast you move. You do that over and over again, but you move it up or down. That's like a voltammogram. Okay. And then there's, I'm not sure if you didn't ask about sampling, but this is more of a software thing, but it's relevant. I mean, it does affect the thing. You did not ask about that. That's less of something that you're concerned about. Basically, what square wave is doing is, or what the instrument is doing, I should say, is, let me start inking. I can kind of draw. Let's see. I'll pick a color you can see. So the potentiostat goes up to here, and then it holds it for a bit, and then it measures a point, and then it drops down, measures for a bit, and then it measures the point, right? This is I1. This is I2, current. And so what it reports is at the end of this whole thing, this is I think it was like 33 milliseconds, that whole sample. It reports I1 minus I2. Okay. So that's like I'm not trying to draw absolute value. I'm just trying to like square it up. Sorry. The point is that like this is the current you get with square. It's actually a differential. It's like a difference of current. And the reason is it's sort of like a subtractive process. Like it's a way to get rid of background processes like built up of double layer capacitance or what have you. Okay. And so, each of these steps here, these flat steps, is like a chronoamperometry. Words.
Yeah,
words. And things and stuff.
It does sound weird. Amperogram.
Amperogram. Yeah, we don't say that very often. That is a word, and that's what you call it. So, like Alex drew before, that's each time you and it's not long, like it's milliseconds, but each of those is technically like a little decay curve, right? And then so the current is decaying or whatever, and so you're basically like subtracting, and whether it's upside down or right side up. Don't worry too much about the specifics here. The point is like this amount of current minus this amount of current is kind of like taking away that background, that charge, that non-Faradaic charging stuff. It kind of helps you clarify, in your case, what is the ferrocene on your self-assembled monolayer. So you're studying just the Faradaic process that you're after. Okay. So now to the point of your question, I haven't forgotten. So how to choose a particular like amplitude, frequency, and step voltage. Okay. So in some ways you can kind of think about it in terms of cyclic voltammetry. Okay. So as a comparison, so this is like all of the things, the amplitude, the period, and the increment. So the effective scan rate is the increment divided by the period. So the increment is exactly what you see here, how much you're moving up, and the period is this. So one answer to your question is, if you're trying to maybe, for example, do square wave voltammetry in a comparative manner to a more common technique like cyclic voltammetry, then try to work out parameters that might be analogous, to cyclic voltammetry. So like in this example, I did 8 millivolt increments with 33 milliseconds. That's like 240 millivolts per second. It's actually pretty fast. So you could decrease your increment, and that's like an effectively slower scan rate. You could increase the period, and that will decrease your scan rate as well. So the things to be considering to answer your question that you're doing is, the longer your period, the more you're letting that like decay, that chronoamperogram stuff happen, the more you're, I don't know, you could think of it like effectively subtracting out stuff.
Yeah.
Okay. So that's one thing. Now, that is entirely dependent on the time constant of what you're studying, which I don't know. You might know better than me, of course. But if the self-assembled monolayer ferrocene whole process has a very quick time constant, like nanoseconds, microseconds, like really, really fast, like then you don't need to have a very long period, for example, for it to like be settled out or whatever, right? That might happen almost instantly. But if it's a slow process, you might need a longer period because you want to you might not be subtracting accurately if you don't give it enough time at each potential. So that's one bit. And then the increment is really like, if your increment is too big, you're going to like miss something. Like if you increment like 50 millivolts, you might skip right over some Faradaic process, right? Because you're going,
it's like losing resolution.
Yeah, exactly. Like the resolution isn't high enough. So in some ways you can say you want the increment to almost be as small as possible. It's just that makes the scan rate really, really slow, right? Like if the increment is like a microvolt, it's going to take absolutely forever.
Yeah.
You know?
Yeah. To see everything.
Yeah.
But it'll take forever.
So that's like a trade-off on the timing that you want to sit there with your experiment. Right. And the resolution that you're after. Okay. So that's kind of with the increments. I'm just trying to like the amplitude, and then the amplitude. That's a trickier one. I mean, you want, let's see.
So like, it's like, I don't know. Cause I think with like the amplitude, you're trying to go back and forth between like a quote Faradaic and then the non-Faradaic like area.
So this is something that's probably more elucidated with trial and error, honestly.
Yeah.
A lot of that. And then, like for example, if you do cyclic voltammetry and you get a nicely like 60 millivolt separated thing, that might infer that, whatever amplitude is enough, like this is a total like 20 millivolt amplitude is 40 millivolts between the positive and the negative. That might be enough to be like the upper part is at a Faradaic process. Yeah. The lower part is like a little before it.
Yeah.
It doesn't have to be like
to push it down so that you can properly subtract out any double layer capacitance and remove like the because you're trying to get that difference to be the actual incremental amount of Faradaic current.
And so if your amplitude is like really, really small, your current is going to be zero because it's like the same up and down. So it has to be large enough. But if it's so big, you're subtracting like one Faradaic process from like one way before.
Yeah.
So there's this, that's why it's somewhat of a trial and error thing.
Yeah.
But yeah, exactly. You want to, like Alex said, you want to subtract that non-Faradaic process. And so you're judging that based on, in some ways like the reversibility of the thing that you're looking at. And so as far as numbers are concerned, 20 millivolts is a decent guess to start with for like a typically well reversible process, which probably you're doing ferrocene, it's probably relatively well reversible.
Yeah.
So there's a little bit of a discussion for you on that. Hopefully that answers your question about square wave.
Some other things to kind of note, like I don't know enough about like immobilized Ferrocene SAMs, but like the self-assembled monolayer has a certain like length to it, right? Like the monolayer like can be kind of big, and how well ordered and packed it is. And all right, maybe there's some molecules kind of inside that monolayer that don't really move very much when you're stepping the potential up and down from your square wave. So how long your self-assembled monolayer is, like the chain length of probably a thiol that you're using, is probably going to play a role. I would guess shorter self-assembled monolayers where the ferrocene and the enzyme are closer to the surface, you probably can get away with shorter increments or shorter time periods than if it was like super long and like it actually takes a while for the electron transfer to go. So that's some other things to think about as an experimental parameter.
Do you want to answer the Twitter question?
Yes, I do want to answer the Twitter question. This is again from Umar Latif. If the potential difference between oxidation peak and reduction peak is greater than 0.1 volts, can we establish a diffusion phenomenon in our active material? And the answer is no. So the reason why is like, the value of the potential difference actually doesn't have that much to do. It has a little bit to do with diffusion, but there's a better way to determine if you have a diffusion controlled process. And that's to use the Randall-Sevcich equation and do a scan rate study. And so the Randall-Sevcich equation briefly has like the peak current in your voltammogram is equal to a bunch of constants, has to do with concentration, area of the electrode, number of electrons, Faraday's constant, the diffusion coefficient, and the square root of the scan rate. And a very common application or a very common way to determine, hey, is my molecule diffusion limited or diffusion controlled?
There it is. Wait.
So
we're talking about it. I'm like, I'm gonna pull it up.
Yeah.
There's a million different.
There's different versions of it,
but
but
why didn't it get bigger?
Yeah, it's like that. It's like only your browser's getting bigger, but the images. Well, it's okay.
This is some website anyway. So there it is.
But yeah, if you can do a scan rate study where you look at peak current versus the square root of nu in that equation, that's a better way. The peak separation itself isn't really enough. And usually if you have 100 millivolts as the peak separation, you probably have some solution resistance or something in the way if you have like a purely fast electron transfer process. Of course, I don't know enough about your system, but just because you have a peak separation that's greater than 100 millivolts, I don't think that's enough to say for sure it's a diffusion control thing. So square root dependence of scan rate, I think is better. And if you don't get a square root dependence, you get like a log dependence, then you have like a surface bound thing. So that's another mass transport thing that you can use. So Umar, hopefully that helps. That helps. Let us know if you have any questions. I am keeping an eye on the Twitter feed as best as I can. So
yeah. So Omer has a question. How activation energy barrier increases or decreases when transition state is similar to reactant or product in the case of electrode processes? Activation energy barrier increases or decreases?
Let me see. How activation energy barrier increases or decreases when transition state is when the transition state is similar to reactant or product in the case of an electrode process. Well, the activation barrier should be
independent of
very similar. Well, it depends. So, okay. Well, this is my limited understanding of it, but
I guess I don't totally understand the question is part of my problem.
Yeah. So if you draw reaction coordinate, so this is reaction coordinate. God, writing is hard. And then you have energy. Let's just call it E or something.
Don't write out the whole word.
Yeah. So sometimes people do. So in a very simple case, it's like, okay, you have reactants, and I'll just use an R, and then you have products, and then you have, you have to have, this is your activation energy up here. And then this guy right here is your transition state. So this is transition state. And your question, let's see, transition state. And your question, so this is kind of the picture that we're working with, right, when we're thinking about it. And the question has to do with, let me go back to the questions. How the activation energy barrier increases or decreases when the transition state is similar to the reactant or product in the case of electrode processes. So if it's similar to the product, if it's more similar to the product or similar to the reactant. I would say, I mean, you might be right, Neil. It may be somewhat independent, but
I mean, it's like I haven't seen this diagram quite as often. I'm not as familiar with the transition state phenomenon, to be honest. I'm more, if you were to have drawn one hump from reactant to product, that's what I'm more familiar seeing.
Oh yeah.
And so the EA is that hump.
Yeah.
Right. They have to go over to get from reactant to product.
It's similar. Which it's close enough.
This is not. I don't know if this is the difference between chemistry and chemical engineering. I didn't learn this.
No,
as much. So, but my understanding of activation energy, sort of in general, and it probably at least related to this transition state phenomenon, is that it's kind of an independent phenomenon. Like any process, regardless of its difference in energy between reactants and products, regardless of whether it's endo or exothermic, can have a large or small activation energy. It's kind of its own animal, right? For lack of a better, term, I guess. It's like it's its own thing. And so my interpretation, or my, I don't know, you say guess, like educated guess or whatever, is the answer to your question is that it doesn't. Like it's independent. Maybe that's wrong. Like maybe it would affect it. But my impression is that the activation energy is somewhat of like it's like an intrinsic thing. It's its own, it is what it is. We measure it and we tabulate it. You can find activation energies like tabulated for different processes, right? And it's like, if there's a transitional state that's closer to a reactant or product, it's the same as if the energy state between reactants and products is close by itself. Regardless of a transition state, you might still not be able to get from one to the other until you overcome the activation energy. So it's like, it might still have a big activation energy, even though where you're going is the same as where you came from, right? Like energetically, if the transition state is right where your R is, it almost feels like, well, why is there an activation energy if I'm going from one energy state to the same energy state? And it's like, because it just is. I don't know. I don't know how else to think about it.
Yeah.
Maybe you have more insight or
something. So like this is my very limited understanding of like at first it's a theory. It's like transition state theory, and it's the idea that like, let's say you had A plus an electron goes to B, right? So that's the reaction. But what people really think is that it's more like A plus electron goes to like A star. A star is like
transitional thing?
The transition state. And so some people think of it as like, well, I'm going to play around with, this is not real, but like, let's say I had water. So if I have water, it's these two, electrons, and I have, and we have this nice like bent configuration or something like that, right? That's how we learn the structure of water. The transition state for water, I'm 100% making this up, is like water goes like this. It's like linear. And so to a degree, like I
can see
it
it
away from it, but it's like, oh snap, like water goes from a bent to a linear configuration, high energy, to get this to happen. And maybe there's like an electron or something here, and then it converts to whatever the actual product is, which is B. So linear water turns to B. And so the question, to my understanding of what this guy's trying to ask, is like, hey, this linear water is so much closer to what bent water looks like as opposed to what B is.
Right.
How does that affect like the energy, and in a way his question is, how does the activation energy barrier increase or decrease? And I think you're right, Neil, which is that the activation energy barrier will be the same. It's going to be the relative position of the reactant and the product. So like, this might be closer to the transition state, or this might be farther from the transition state. Just the movement of these near the transition state is really what it's going to represent. So that's kind of how I think about it.
And disclosure, we could be wrong.
We could be wrong.
This is our interpretation based on our knowledge. But yeah, I don't personally have a lot of real study or experience with this phenomenon, and so I might very well be wrong. But that's my impression. So I hope that's the right answer. I'm sorry if it perhaps there's a better explanation. But that's the best that we, I guess, can answer for you.
Yeah. I'm literally just drawing upon like what someone told me in a kinetics grad class from like it feels like almost over 10 years ago.
Yeah, at this point it's getting farther and farther into the past. It's becoming harder and harder to remember it sometimes. Remember
what those things are.
Yeah.
But anyway, hopefully that's helpful. He's thinking about this stuff.
All right, let's see. Race has another follow-up here. I'm planning to perform EIS on a battery module. What should I interpret if I obtain a smooth output result? EIS, since EIS data cannot be break down from the module to a cell level. I don't know. What do you mean by? I need you to elaborate what you mean by smooth output level.
Yeah.
And I guess by module you mean it's like an RS configuration of some kind. I kind of don't. I'm kind of not sure the context of what you're asking for. What are you doing EIS on? Like a battery module is just some series and parallel configuration usually, but it's still probing the battery processes, I would assume. So
is he referring to like if you have like a couple individual cells and you stack them together?
Yeah, that's a series parallel.
And he's calling that whole thing the module.
I'm guessing. I'm guessing. Yeah, like so it's you call it like an SP. I think it's an SC to say SP configuration. Like people will like this is how like like a Tesla, right? Like a car. It's like a billion AA batteries.
Yeah.
Basically. Yeah. Right. It's like the entire frame of the car is just like a billion AA batteries, kind of, in a various configuration of series and parallel. So you put them in parallel and you boost the current while keeping the voltage the same. And if you boost them in series, you increase the voltage while keeping the current the same. So that's how like a 4-volt battery that gives you 1 amp, you can get 20 volts and 6 amps if you have 5S, 6P, whatever the numbers worked out. I just made up numbers and I probably didn't say the right S and P. But that's when you gang a bunch of them together in series and parallel configurations, you bump up the voltage and the current accordingly.
Oh,
so I'm guessing that's what you're talking about.
Race has a comment
what's
at the bottom. It says,
module is a collection of cells,
battery cells in series.
So it is what I'm talking about in series and parallel. So I guess I don't understand what you mean by you get a smooth result. I mean, if your question is like if you do impedance on like the terminals of that, you're just probing every cell. So sometimes what people do is they do this, like, and this is what, honestly, what a lot of times a battery management system is doing is it's probing the whole darn thing, which is dangerous because sometimes it's like one of them can be severely overcharged or over discharged, but you can't always tell because it's sort of averaged out in the S&P configuration. But what you'll see is some distortion in part of the EIS. For example, if you do impedance on the whole thing, you'll start to see some distortion. And it's like, you can think about it as like follow the pathway of the circuitry, right? It's going through all of these batteries at once, basically. And in theory, if you have a battery module, they're probably they should, hopefully, unless your battery is doing a really odd job of it and behaving poorly, they're all ideally roughly at the same state of charge at all times. They're all being evenly discharged and discharged if a battery module would in theory do that. So it's like I guess I don't understand. You can try to fill in. I'll go to the next question. Well, maybe if you have some more, I don't understand if you obtain a smooth result, like you should get a decent impedance result, I guess. It's going to be some series and parallel aggregate of the capacitances and the resistances therein, but you should still be able to get a result. I would assume. Like, I don't understand why you think you wouldn't get one. I guess I don't quite understand. But feel free to give some more details if you want.
Yeah.
Chris was talking about the square wave sampling at high frequencies at edges to see transient effects as well.
Oh, that's like an application of square
yeah,
wave.
I think he commented while I was talking about square wave. So sorry, kind of getting to the comment a little after the discussion there. But I mean, yeah, in theory, I suppose sampling really fast, it's like increasing the frequency, and you can kind of maybe see some of those effects. But again, my point about the speed being on par with the time constant that you're studying, and like Alex was saying, like sometimes those long stuff monolayers might take longer or something like so. The frequency or the period with which you're doing your square wave, being somewhat on par with the time constant, of what you're studying is ideal or whatever, because if it's too fast and the process isn't like finished, you're not getting any maybe as much useful data or something like that. So okay, Tarek is back.
Tarek,
good to see.
It's been a while.
Tarek, it has been a while.
Yeah, welcome back.
Let's see here. In a Nyquist plot, what does it mean when a linear capacitive line starts to deflect in the low frequency range? What circuit element is most suitable? This is a weird phenomenon. I've seen this before. I have no idea. I don't know why this happens.
Is it like the capacitive line just starts going like the opposite direction?
It goes sideways. So let me draw. Tarek, I think what you're talking about is this really weird, crazy phenomenon. Hang on. Let me delete this nonsense that I drew before. That's all garbage. Okay. So in a Nyquist plot, it's like, you might ideally get whatever. That's a terrible semicircle. Okay, semicircle and diffusion. But sometimes you get this weird behavior where you get like semicircle and then it just does this.
Oh, yeah.
And it's like, there's nothing. The answer to your question is what circuit element? Nothing. Like literally nothing. An infinite series of RCs in theory would do that because it's like ganging together a bunch of these with really, really small alphas would in theory make an infinite kind of flat line. But that doesn't make any sense. Like, are you really going to describe it as 40,000, charge transfer processes all gang together? Like, that's probably not what's happening. This is not, this is almost like a CPE where alpha is like almost zero. Because if it's actually zero, it's kind of just a point, because as I've showed before, a CPE where alpha is zero is just a resistor, which doesn't behave that way. So it's almost like if your alpha is like really small, it's like, very, very tiny angle here, like, 10 degrees or something. But like having it go perfectly flat, as far as I'm aware, when you do Kramer's Kronig on a data set like that, it doesn't match. Now, maybe yours does. I don't know. But I have yet to understand, if that's the process you're talking about, what that actually is, if it's anything real. My hunch is that it is not. No, I mean when the red curve starts to deflect. What do you mean by deflect? Can you describe what you mean by deflect? Deflect where? I don't
frequency range.
I don't understand. Yeah, I know what you mean by the red curve. So okay, so you're not talking about the flat thing that I said I don't understand. So that's good. But the red curve, which is like the regular one I drew poorly, but type what you mean by deflect. I don't understand. Let's see.
You're also a YouTube member, so you can actually join us.
That's true.
And on the live stream, there is still a link on the YouTube community.
Yeah, I don't know what deflect means.
So
you mean go backwards? If you mean go backwards, I have an answer, but I don't know what that means. But I'm not sure if that's. Picture a theoretical 90-degree live.
90-degree line curving to the right.
90-degree line curving to the right.
Inductive loops.
Are you talking about? Is it an inductive loop? Is that?
Nah,
I'm
just joking.
I need you to draw this for me, Tarek. I don't understand.
Yeah.
A 90-degree line. So 90 degrees. Hang on. I'm going to share. I'm going to try to draw what you wrote. It's going to be a disaster, but I'll try. The red one. So forget about the blue one. So 90-degree line like that. That's 90 degrees, and that's the right. So is that what's happening? Like, first of all, if you have something like that, like a sharp curve, that's also like impossible. That doesn't happen. I don't know what that means. So, I mean, if it's going back down like that, if that's what you're talking about, I mean, it's like, this is almost like a semicircle, right? But it's not. And it's like diffusional heading straight down. I also don't know what is going on. That's a very, especially at like really low frequency. The tricky thing in general with this whole idea is that at really low frequencies, like 100, what did you say, 100 millihertz? Is that what you wrote? Sorry, I was trying to find the original comment.
Oh,
yeah, 100 to 10 millihertz. Yeah, like when you're doing impedance that slowly, there's so many possible drifting and diffusional effects and things like that that can make the data wonky and possibly violate impedance. And so the data aren't always guaranteed to be valid impedance anymore. So very possibly it's something like that. I have seen some few instances where there's some odd stuff happening, like it actually curls up and back towards the origin almost. And it's I can't even remember the specific details. It was, there was one customer that had some data like that. It was very, very strange, and it was reproducible. They could produce it again, but it was like it was one of these odd, it was one of these odd explanations that you hate as it relates to the inductive loop. It was something like, oh, it's like a radical under deposition, like, I don't know, something, right? We're just coming up with terms like somewhat esoteric electrochemistry related or physical chemistry related terms to explain some weird phenomenon we're seeing, and it's like, but what's happening? Like, I don't know. It's like film something, or I don't know.
I have learned weird. A little bit more about what causes inductive loops. And
it's inductors, really tiny inductors.
But there's actually an equation. It's in Mark Orzum's book.
Yeah.
There's an equation that relates the inverse of the induction to some constant, and then there's a lot of math, but involves like these surface reactions and like literally electron transfers between and this explains corrosion like perfectly. It's like, oh, there's actually a 1 electron transfer from like iron neutral to iron plus, and then iron plus to iron 2, and then iron 2 goes out, and it's like that whole thing. It's like there's several connections. I gotta read about it and learn more, and probably ask Mark Orzum a lot of stuff.
That's like the other made up answer of like surface relaxation of species. It's like, what does that mean? I don't know. Mark Orzum maybe described it, but I still don't know. So something like that. I guess that's an answer.
Yeah. All right, let's see. Barry has a question. I think actually there's no question mark, but he says, thank you for the answer. You answered it. It approaches 0. I was talking about chronoamperometry. HEC, I think he meant HER, hydrogen. Actually, no. Hydrogen evolution reaction. Reductive current, when I reduce H plus to H2, then the slope is very odd. But I should be able to suss out diffusion rates for all species. If you're doing chronoamp, I mean, one of the things about converting H2 or H plus to H2 is that H2 is a gas. It just bubbles away, which means that your diffusion layer thickness is kind of in an amorphous state. Like you're almost not forming it in a way, because once you form hydrogen gas, it really floats away, and you now have new H plus near the electrode surface. If you're looking for diffusion rates, I don't know, you may consider other techniques like EIS or a rotating disk to suss those out. But yeah, I could see how chronoamp might give you a weird value when you're looking at H plus to H2.
There's actually a method with chronoamp to suss out diffusion rates called current pulse relaxation.
Oh, really?
Yeah. And it does involve long-ish times. I don't know how effective it would be with HER for the reason you just described, because hydrogen is so fleeting.
Yeah.
And it's like gone immediately, and it's a mess. It's hard to deal with in that way. But in theory, you can suss out, actually, the way Barry is talking about, there is a way to get like there. I did it actually. I was in graduate school, but it's like there's a way to relate the Cottrell curve, the diffusion, the decaying curve to a diffusion, and whether it's just the Cottrell equation itself. I mean, it's sort of a variation of the Cottrell equation, because the diffusion coefficient is in the Cottrell equation.
Correct.
And there's some other fancy schmancy stuff you do. You fit it to a thing, and anyway, I don't know the specifics. I did it again forever ago, but I did it, so I should know it with more authority than I am displaying now. But there is a way, in theory, to get the diffusion coefficient and stuff like that from chronoamp. But yeah, I mean, you could also try stuff like impedance or rotating experiments to get another method, for studying the diffusional things. This is a pretty quick one here. So Gaurav asks, in an electrochemical cell, which is the negative electrode? Is it the anode, because electrons are being transferred to it? So this is a terminology thing. So the answer to your question generally is yes, the anode is the negative electrode. Those terms are used interchangeably, anode and negative electrode. Like if you're looking at an actual battery, like a battery you buy at the store, the minus side is the anode and the plus side is the cathode. Batteries are defined, anode and cathode, by the electrodes that are either receiving or giving, so transferred to or away from electrons during the discharge. Okay, so everything about your question is correct, except it's the opposite at the end. So the negative electrode for a battery, an electrochemical cell, it's different. So let me back up one bit. So in an electrochemical cell, like a glass cell with sulfuric acid and like 3 electrodes sitting in it, you just don't really use the terms anode and cathode. It's not really applicable. It's really more of a battery or a capacitor or a fuel cell is what it's used. But for a battery in particular, when you're discharging, the negative electrode is called the anode, and that is the electrode during discharge when electrons are going away from it, not to it. Okay. The cathode, conversely, is the positive electrode, and during discharge, electrons are going towards it. That actually sounds backwards, but that's what it is, because it's positive and it's going towards it. It actually, so maybe the better way to think about it is during charging. I don't know. That's the correct designation. I don't know why. Probably the way I described it is less sensible. It's actually during charging, the anode is the one where electrons are going to it. So it's the same. It's just that during discharge or during charge, and then it's tricky because like a primary battery, I designated it with discharge because like primary batteries can't be charged back. So I'd sort of think about it as a discharge process. But anyway, for what it's worth, the anode is the negative. That is the designation we use. It's somewhat arbitrary, again, because you can oxidize or reduce anything, you can bring electrons to it or take them away if you're oxidizing, depending on what you're doing. But for what it's worth, those are the things that are happening on those electrodes, is that while you're charging a battery, again, electrons are going into the anode, the negative electrode. While you're discharging, it's the opposite.
Very good. There is some comments, a nice comment from Chris about the transition state for like if it's passing through a catalytic process. Ray's actually has a clarification from his question about
the module thing. We talked about, there's a series in parallel. Yeah, I think.
Yeah. So I think I guess the question from Race is just like, can you do EIS of a module and get information about the individual battery?
Oh, this? No, not really.
Yeah, that's what I was figuring.
No, you can't.
Because it's all average.
The best that you can basically do is get a bird's eye view of, is something wrong or what's going on. You can't really deconvolute very easily which is why some advanced battery management systems are wired in such a way, I don't know if it's like a multiplexing thing or they just have it, whatever, but it's like, let's say you have 100 cells in a battery module, and you can like get its voltage and its current at any time, and you can do impedance on the whole thing. Okay. But then also let's say this 100 battery module is let's just say simply like 4 sets of 25, whatever. Okay. Then in theory, what would be more valuable is you can get like the individual voltage, current, or impedance profiles of each 25 cell module also. And then that way, if like your 100 cell EIS data or whatever data looks kind of bad, well, which you can either scrap the whole thing or you do individual 25 A, B, C, and D, and you find that C is in bad shape, but A, B, and D are fine.
Yeah.
And it's like, oh, well, I'll just replace this one. Now make that more granular. You have 5 and 5 and 5. Like, you see what I mean? It's like, in theory, the best battery management system for a module of N batteries would be able to individually probe each battery, because if something goes wrong, you can replace just that one battery. But that's not really practical. That's actually quite programmatically difficult. It's hard to wire it that way. There's a lot of issues with doing that. But the reason why you would, in theory, want to do that is the reason to answer your question, which is that no, you can't really get a lot of cell level information by doing a module experiment. You can't. The circuit necessarily includes everything, So Armour has a follow-up too.
Yeah.
Butler-Volmer, what is this?
Yeah, so he's talking about, so thank you, boys. In Butler-Volmer equation, there's a term called the transfer coefficient, which indicates whether transition state is similar to product or reactant. In the presence of electrochemical double layer, the activation energy is affected. And it's true, actually. So I had a short little thing I can share about this. I looked at this ahead of time. So can you see my screen? So
yes.
Yeah, so there is this transfer coefficient. And so if this was it's kind of a stick drawing, but all this is taken from Bard and Faulkner. But if you had your standard free energy, the reaction coordinate, you have an alpha coefficient. And then when you make the potential more positive, you drop this down. And this is a case where alpha is equal to 0.5. And then if I change the slope a little bit more this way, this is when alpha is less than 0.5. So this is when you're kind of changing the slope. And in this case, it's easier. The activation energy getting from reactants to products is easier. So yeah, that and you can do that the same way. You kind of shift it. With the alpha transfer coefficient, if it's greater than 0.5, it tends to favor more formation of the reactants. And of course, this is for just the reduction reaction here. So that's just what alpha represents. How it affects the activation energy, I think.
Is it related to the activation? I actually don't know 100% the what would you call it? The derivation of the alpha, but it stands. It seems to me, based on alpha and what you're just showing about how it kind of affects the transition between the reactants and the products, that maybe the alpha is actually tied to activation. Like, is there an equation? I don't know, to be honest. I'd have to look in textbook or something, or looks. Is there an equation that relates alpha to activation energy?
I think,
is it an Arrhenius? You know what I mean? Like, is it the Arrhenius equation is where activation energy is often used? Like, is alpha an Arrhenius thing? There might be something there that I can't.
It shows up in the Butler-Volmer equation in the sense that you always have this
1 minus alpha.
It's 1 minus alpha
for the oxidation and the reduction part.
Yeah,
for sure. But I'm saying, like, how you get alpha itself, is that related to the Arrhenius equation?
Oh,
you know what I mean? The alpha constant,
how you get the alpha constant?
Butler-Volmer, that Butler-Volmer alpha. I don't know, Arrhenius. I'm wondering if that's like how you calculate it. Charge transfer coefficient.
Yeah.
Is it related to activation energy?
I mean,
I don't know.
It definitely, like, the alpha transfer coefficient definitely gives you. I mean, it's the slope. That's what it represents. It's the slope of that line, and when you move potential, you're moving this thing up and down. But when it has a different slope, it means it has a tendency to favor more products or favor
But like
reactants.
even with your stick diagrams, for example, and I'm drawing this to you in space here, but it's like
right.
those two slopes. If you were to draw that hump, that's like the activation energy. And so if the slope decreases, it's like decreasing the activation energy.
Yeah.
Like visually, that's what I'm seeing. If the slope changes, it's like you're decreasing. So it's like alpha appears visually tied to that hump size, which is like the activation energy. So I'm wondering if there's, and I'm just looking quickly. I don't see. Maybe it is. Maybe it's not. Maybe I'm off base here a little. But I'm wondering if that's somehow a thing. Yeah, I see. Assume the rate constants are in Arrhenius equation. That's not exactly the same. So anyway, I don't know. Maybe that's not a thing, but that's just what occurs to me.
Yeah,
which would be sort of an answer to that question, or what Omer has said. Is there some transition state related to the EA? That kind of thing.
Yeah. And to a degree, there is activation energy also has to do with the kinetics, right? When the kinetics are, like if you have a low activation energy barrier, your kinetics are more favorable. And if you're looking at a reversible electron transfer reaction and your alpha is greater than 0.5 or less than 0.5, it's going to mean that the propensity, the rate going one direction is going to be different than the rate going in the opposite direction.
Yeah.
Now, interestingly enough, I would say, I was talking to Jillian Dempsey about this, but it turns out most molecules, most of them actually have an alpha of 0.5.
Oh, really?
Yeah. Just like in general, like
interesting.
You can change it around, but most molecules tend to have an alpha of 0.5, just like, I guess, experimentally, as well as from simulation.
Interesting.
And we could simulate. We could actually show you what those kinds of voltammograms look like when you change the alpha.
Yeah.
But usually it will manifest itself more so when the kinetics are slow. So it's when the kinetics are slow, the heterogeneous rate constant is slow. That's when you'll actually see visual differences in your cyclic voltammogram, your experimental data, is when if alpha is not 0.5, it will manifest itself when the kinetics of the electron transfer is slow. So I don't know if that helps a little bit more with Omer a bit about that.
Yeah. Okay.
All right.
So let's try to get through some of these because we're running out of time.
Yeah, that's right.
Thank you for the questions, everybody. We'll try to
to get through as many as we can.
Yeah, Esteban says, thanks for opening up this space. Thank you for joining us. Appreciate it.
Yeah.
Is it possible to perform EIS on a zero gap MEA electrolyzer? What does zero gap? Does that mean band gap? I mean, if what you're talking about is that it has a zero band gap and it's fundamentally not conductive, then no. You have to, something has to be, you have to have electrical conductivity to be able to do. Now, if you're talking about doing impedance to determine the conductivity in terms of ionic conductivity by using other electrodes, like a 4-point probe experiment, then yes. I guess I don't know exactly what you mean by zero gap.
I think I'm just kind of looking at membrane electrode assembly. So
yeah, that's a fuel cell thing.
But it's just like, do they just stack them super close to each other? So that
membrane electrode assembly consists of the anode and the cathode basically pressed into a membrane, and there's a catalyst in the middle there.
Okay.
So, but is that what you mean? Zero gap?
Yeah, with a gap, like, it's just like.
Do you just mean that it's tightly pressed?
Maybe that's the question.
Yeah, I guess that's part of my hesitation is I don't entirely know what you mean by zero gap MEA electrolyzer. Zero gap, like if it's tight, like most membrane electrode assemblies in an electrolyzer or a fuel cell are like, it's literally like it's a membrane, and then you paint platinum on carbon on both sides, and then you press carbon paper on both sides. That's the gas diffusion layer.
Yeah,
and so then it's
hard,
and then it's pressed together. Yeah, exactly. And you flow gas on both sides, and you do your thing.
Yeah.
Like if your question is generally speaking, can I do impedance on an electrolyzer? Yes, you certainly can. If there's some other,
so we got an update.
Is there an update? Okay,
yeah.
Good, let me see.
There's no electrolyte instead of that. They use gas diffusion electrode.
So instead of electrolyte, they use a gas. So is that what you mean by zero gap? Like there's no electrolyte? Let me see here. For CO2 reduction, gas diffusion electrode. It is possible. Like this sounds like a solid state system, I guess. If there's no electrolyte, gas diffusion electrode. You can do impedance and you can do electrochemistry in solid state systems. You don't have to have an electrolyte. There just has to be a way for the circuit to be complete. So, I mean, I think the answer is probably yes. I don't have a lot of familiarity with this system exactly, but probably yes. I mean, if it's actually an electrolyzer and it's used to generate CO2, or I guess electrolyze CO2 and generate whatever product, probably yes. In fact, EIS is a way to get information about systems like this that it can be quite effective, because you can you typically, like if you have
so does that mean that's like both, like a gas diffuse electrode is just like a very porous but conductive electrode,
something like that,
being pressed against
another
a
one,
non-selective membrane or something,
and there's no,
and then that's pressed to like the anode, the other side.
I mean, I think
the gases
so.
are just diffusing
I mean, usually what that process involves for an electrolyzer or a fuel cell is what you just described, but the membrane is soaked with solution of some kind, like electrolyte.
Oh, okay.
Right? And so that's the ion bridge between the anode and the cathode.
Yeah.
And so in this case, the ion connection between anode and cathode is whatever free species can move in the ion selective membrane or something. Like there's got to be some species, there's got to be some plus or minus that can move between anode and cathode, right? I mean, otherwise, so I mean, effectively, if it can behave electrochemically at all, then you could certainly do impedance on it. I mean, in theory,
but you would just make sure you have a steady state with whatever you're doing when doing EIS, I presume.
Yeah.
So that's stable. Let's see.
Tarek was filling in some more details about this odd thing. Theoretical 90-degree live. Okay. Visualize a diffusional straight tail making a 90-degree angle with the real axis. It gradually levels off, almost resembling the state of a new semicircle. So like this, that's the 90 degrees. So it goes straight up and then it tails off. Yeah, I still don't know what that is. But I guess, I mean, it could be a really, really large Randall's element. This is a really big R. You know, and I mean, it depends how sharp this part is. Like if it's like straight up and then it like just starts to level off, that's weird. I don't know. There's no circuit element that really captures that. If it's like straight up and then it really kind of starts leveling, whatever, you know, that just sounds like a regular process. It's just a really big, you know, like Randall's element with an extra diffusional element, whether it's in line or not. Like that's kind of what it sounds like. But if that's not fitting, you know, there isn't really any other circuit element that exactly captures that behavior either. So all of these made up drawings I'm doing are not exactly easy or obvious, I guess. But yeah, it's a bit of an odd phenomenon.
Yeah. I'm just responding to somebody on Twitter.
Yeah,
right now.
no worries. Let me know if there's any other Twitter questions. Are there plans to enhance the level of customization available when configuring a transmission line model in our software? No, and the reason is that we already have the most customizable one on the market, as far as I'm aware. We allow you to customize the boundaries and the interface and whether or not you have a resistor through the pore, and whether you have a leading inductor or a leading resistor. As far as I'm aware, there's no other software that allows you to adjust all of those. It's not feasible to create specific models that are valuable for simulating restrictive diffusion? Yeah, I mean, unfortunately, Tarek, there's always more things that could be modeled or done. And as a commercial software, we simply don't have the scope of the, resources to make it that customizable. Those kinds of things are likely, you have to write your own subroutine or something for that. Again, as I said, to the best of my knowledge, unless it's changed, I'm somewhat aware of, I've used many of our competitors, for example, in the past and things like that. And I'm, moderately aware of what they offer. And most of our competitors have some form of a transmission line offering in their software, but I don't know that anybody's, as of however long ago that might have changed. Of course, there might be other stuff that I'm not aware of now for sure. But to the best of my knowledge is that most people, our software competitors, have like a couple of pre-canned transmission line options and not a lot of tremendous customization, which is why I advocated for the one that we have in our software now, being pretty customizable, but that's about the extent of it. It's actually tremendously computationally intensive to even do what we have programmed. And going further along that line is probably not something we're likely to be doing for a variety of reasons. It's not likely to find as much widespread interest. While it probably has a lot of interesting aspects to it educationally, I don't know how applicable it is to the wider, customer, like our customers. Right? There's a financial and a marketing aspect to this. Of course, we're a company and our resources are somewhat limited to develop, what we choose to develop, and that isn't likely something that would be something that we could put a lot of resources into, to be perfectly honest with you. Not to say it's not, of course, scientifically interesting, but yeah, what could the very large resistance mean? To your point about that, odd, it goes up and then it starts to curl over. It might just be an odd manifestation of the diffusion. And one way to think about diffusion as you go to lower and lower frequencies is that it's like it like is analogous to an ever increasing resistor, because the diffusion layer thickness is growing. And as the diffusion layer thickness is growing, its impedance is growing. Like and so that's kind of like, they're analogous. It's like an ever increasing Randall's element resistor, sort of like it's a similar phenomenon. So it might be something like that. It's a diffusional. Also, it's like a growing, diffusion layer. And so its impedance keeps growing and growing and growing, like the Energizer battery. I don't know. So something like that is my best guess. But again, it's like without seeing the data, I'm not 100% sure. Yeah. Okay. Ferris has another question. And I'm just kind of rattling these off here. Yeah. Is there anything on Twitter you need to cover?
Yeah, there's a question, but considering the time, I figured we could answer some of these questions like next week. And he said that was okay.
To punt some of these, but
yeah.
If you did EIS on a module with say 2 cells in series, would you expect to see 4 semi? No, probably not.
Yeah, because
because you could imagine if you did like 100 of them, you wouldn't get 100 semicircles. There's going to be overlapping. Most likely, there's going to get overlapping. Yeah.
Yeah.
And part of that again is because in theory, all of your cells are the same,
have the same RC
exactly
circuits
and the same state of charge.
Yeah.
And so you might get some aggregate one that's related to it. And there's a lot of ambiguity here, like whether it's in series or parallel. You might get double the resistance, or the resistance is, it's like the sum of it, it's going to behave in a series or parallel manner, the way like Kirchhoff's laws dictate. So it's like, if they're all in series, in theory, I suppose you would get a resistor that's plus of all, 10 ohms plus 10 ohms plus 10 ohms, you get a 30 ohm resistor, like something like that. If they're in parallel, it's 1 over 1 over 1 over, something like that. And then it's a million S and P, you're going to get some aggregate, like that. All that is to say that you should probably get some aggregate, because it's like similar phenomena in each of the cells, but the summation of those is going to behave in the way of your series parallel configuration. But I know I would not expect to get like a ton of different semicircles like that. The time constants for them are identical. It's the same battery, right? Now, if you had a S&P configuration with a bunch of disparate chemistry batteries, which would be a terrible idea for other reasons, maybe then you would get a bunch of different semicircles, but that would be a really bad idea.
Yeah.
Let's see.
So
Amayapan. Sorry, did you?
Yeah. Oh no, I was just gonna read it. Amayapan. So why the 3 electrode system in EIS better than 2 electrode system when we deal with battery system in particular? Well, I think a 3 electrode system isn't even in a battery system.
Not
Batteries
often.
are all like mostly primarily 2 electrode system.
So the only reason a 3 electrode system, I mean, you could say better. I would say just one of the main reasons why a 3 electrode system is used in a battery than a 2 electrode system is if you want to obtain information about the anode and the cathode individually as opposed to combined. When you have a reference electrode and a third electrode, you do have that ability to, for example, independently study the impedance or anything, the voltage, current. Well, the current's obvious; it's equal and opposite, but the voltage or the impedance characteristics of the anode and the cathode separately, because, but often that's not needed because you're more interested in the battery's performance individually. But the answer to your question is that sometimes you want to get the cathode only impedance behavior, and to do that you can't, like when you have just a 2 electrode system, you necessarily will get the behavior of both. You cannot decouple them. It's a 2 electrode system. It's actually not circuitry and physically possible.
Yeah,
they will both show up. So you can isolate one or the other if you have a 3 electrode system. So that's, but I wouldn't say that's better. It's just a different, you know, if that's what you're looking to study, I guess.
Yeah.
We're trying to answer these quickly here. Let's see. I know Chris was commenting with Ferris on some things. Hopefully you guys kind of worked some of that out.
Yeah.
Let's see. Peace spice.
Yeah, I don't know what pea spice is either.
Is that pumpkin spice?
Yeah.
I hope it's pumpkin spice.
Get some pumpkin spice.
Package like pea spice. Listen, I'm all about pumpkin spice.
And shipping it too.
Yeah.
Packing some pumpkin spice.
Pumpkin spice. I'm a big pumpkin spice fan. I love myself a pumpkin spice latte. It's as basic as they come and I love it. I don't care. That's my jam. That's probably not what you're talking about, but I wish it were. Why don't you cover if there's anything? Umar has a couple of questions. Unless you want to wrap it up here or do it next time.
Who has a couple questions?
Oh, from Twitter, I guess. Or do you want to call it?
Oh, I was gonna
Unless did I miss something in chat? I don't know.
Actually, someone from Twitter mentioned something about zero gap electrolyzers. They said zero gap electrolyzers are similar to fuel cells in design because the heart of the electrolyzer consists of 2 electrodes pressed against a membrane. These electrodes are called zero gap because there is no gap between cathode, anode, and electrolyte. This is from
there's no but there isn't often a gap there anyway. I guess I don't understand the difference.
Yeah,
this
is the BBLT thing. It's like there's bacon, lettuce, tomato, and then whenever you have but it's always served on bread, but you don't call it like a bread.
Bacon, lettuce, tomato, bread.
And bread. Yeah. You don't say BBLT, you just say BLT. Because in the bread world or in the sandwich world, bread is a given. And in the fuel cell world, it's assumed that there's no gap between your anode and cathode. So
I guess that's where I'm lost, is that if there's no gap, if there is actually literally no gap between anode and cathode, that's not a cell. That's a short. Right, that's like if you touch your counter electrode to your working electrode, you touch your anode to your cathode, whatever you want to call them.
Yeah,
that's not a cell.
Yeah,
that's a short. That's just chemistry happening on its own.
Right.
Like the way that the reason we can do anything with electrochemistry and a potentiostat is because we can force the current to flow somewhere else. so we can power our phone, or we can measure it with our potentiostat, or we can run our lights, or we can whatever. Like, you're forcing current to go somewhere that's useful for us. If you just put those two electrodes together, the electron transfer happens right there.
Yeah.
That's just stuff
right.
happening. Like there's no practicality to your potentiostat at all.
Yeah.
So I guess that's why I don't understand this phenomenon of zero. Like, if it just means that, like, that's a term for no electrolyte, then that's fine. Like, that, maybe that is what it means. As the person, I forget who it was here, Esteban, had said, it's no electrolyte. They use a gas diffusion electrode, which is like it's still a separator. There's something physically separating, the anode and the cathode.
Yeah.
Electrically, but it's a different thing. It's not a liquid, soaked polymer or whatever, like Nafion or something. It's a gas diffusion electrode, which is a different thing. Some solid. I don't know exactly what a gas diffusion electrode looks like, or right. I've never used one, but it's some solid thing that's not liquid, but it's still separated, right? It's still like some amount of microns or nanometers or millimeters or miles from each other. Like, it's still separated. So I guess that's why I'm like fundamentally confused by the term zero gap. But anyway. Yeah. So going to sleep. Yeah, you must be a time zone that is later than us. But thank you, Ramzan, for joining us. We really appreciate it.
Yeah, we appreciate everybody.
And sleep well. Have a great weekend.
Yes.
Did you want to answer anything else, or do we want to call it for this week?
I think we'll call it for this week. We can answer other questions.
So Umar, if you're watching on Twitter, thank you. I did see there's some more questions. We will get to these next week. Same electrochemistry time. Same electrochemistry network. Are we back? Yeah, next week should be fine.
Next week should be fine. I think we're good.
Yeah.
And then
next week, Friday at 1 p.m.
Yeah.
Eastern US time.
Yes.
So 2 hours before now.
Yeah.
We will address more questions and be here. And emotes wiping out the message. Yeah, YouTube is strangely bad at the emoji. They don't animate emojis, and it's pretty, listen, Chris, you have to understand, whatever tiny indie company owns YouTube.
Yeah.
Okay. It's a tiny independent company. I'm not even sure if they're profitable.
Yeah.
They don't have, you think that we don't have resources to like deal with these transmission line crazy things that Tarek is talking. You think YouTube has resources to deal with anything? You're out of your mind.
Yeah.
Tiny indie company. I'm grateful we get to use it at all.
Yeah.
Okay.
Yeah.
So get it? It's funny because it's the biggest company in the world.
Yeah.
Oh, sorry, but we have a laugh.
Yeah, we have a laugh.
Okay.
But next week we should have no problem.
We should be here. Yeah, it's like we've had like 8 weeks off, and now we're
or one on, one off. Yeah, it's kind of thing.
It's been a while. But now we're back for a bit. So.
Yes. Yeah.
Anyway, thank you everybody for your questions. I hope this was useful. If you're watching this now or you're watching this later, we will see everybody next week. Take care. Have a great weekend.
Bye.